J, evaporation. Now, I would like to talk about water in this class, and you could say that this class is going to cover what historically is known as sensible heat and latent heat. Now, I'm going to be talking about water, and I want to point out that the first law of thermodynamics applies to all substances. So when we write down, for example, delta U, the change in internal energy, is equal to the Q, the heat that's transferred in, minus the work that's done by expansion of the substance. This is a general rule of physics, the first law of thermodynamics. Now, the work is equal to the pressure times the change in volume. We derive this equation using a gas. We put a gas in a piston chamber, and the gas expanded and the piston moved, and we calculated this. Now, this is true also for a liquid. If you have a liquid in that chamber and it expands a little bit because we heat it, same law is derived. If you have a solid and the solid expands and pushes on the piston, same law is derived. Let me give you two examples from my personal experience. Once when I was a little boy, my dad drove to the local gas station in the Fairview section of Camden, New Jersey. And when he unscrewed the radiator cap, so he was doing some work himself at the gas station, the liquid gushed right up and hit him in the face. And I was surprised as a little boy, in the car, watching that. My dad experienced that. So what happened there is that the heat that was transferred into the fluid because the engine was running build up the pressure, and you can think of the fluid as expanding and filling up any little gap of air that was above the fluid level. And when that cap was released, it pushed everything out. So we have a rapid expansion as work was done, pushing the higher levels of the fluid up in the form of kinetic energy, the work done going into kinetic energy, and it hit my dad. So that's an example. Another example is I put water in a glass container in a refrigerator, in a freezer actually, and I went to go check on it because I wanted to cool it fast. This was not very intelligent. The water expanded and the glass broke in the refrigerator, freezer section of the refrigerator. So what happened there, if we want to analyze it with this equation, the change in energy, in a second I'll want to do something with the Q on one side of the equation. So as the water was freezing in the freezer, you can take this Q to be negative since heat was flowing out of the water. And since the expansion was taking place, because ice takes up more volume than liquid water, this term is also overall negative, because if delta V is positive, then this minus sign makes this negative over here. So you have two negatives here, and the internal energy of the water is decreasing. Now, water is unusual in that it expands when it cools, and when it expands, the molecules are at a lower energy level. They jiggle less and form a crystalline pattern. there. So that's an interesting application of the first law of thermodynamics, and no ideal gas equation has been written down. So we could write the heat transfer as the change in internal energy, and then this goes on the other side, so it's plus W, which is your P delta V. Now, the enthalpy will be important on our discussion today, so let's remind everyone here that the enthalpy is equal to the internal energy plus PV. And we gave this equation earlier. We have talked about this. So let's notice that when we apply the delta to the H, we get delta U plus P delta V. Now we have to use product rule here, and then plus V delta P. Now what makes this very useful is that for the cases where there's no change in pressure, then this term here goes away, and delta U plus P delta V is the same as the heat transfer. So that means Q, and I'll put here a little p to emphasize its constant pressure, is equal to delta H. Now what's important about this is that Q is not a state variable. There's no such thing as saying that the substance has some Q content or value. Q is heat transfer, but the heat transfer is delta H when there's no change in pressure, but H, enthalpy, is a state variable. It's an exact differential. When you integrate, you get path independence, while with Q you have path dependence. So the closest thing we can find to a state variable is the enthalpy related to the heat transfer. But there's another one that we had looked at, and that's the entropy. It's also closely related to the heat transfer. So the first thing we're going to look at here is the sensible heat. It's historically known as sensible heat, and we'll define that. And this is basically heating liquid water. So you heat liquid water, you can sense the change, you can feel it if it's not too hot. You don't want to hurt yourself, but we can use a thermometer to measure the effect that the heat transfer is doing. So that is called sensible heat, can be sensed. Now let's look at the heat capacity of water. So our definition for heat capacity at constant pressure, we want the change in the temperature to approach zero. And we think of this as putting a very little bit of heat into the system and compare it with the change in temperature. And we want the limit as we just do this with a very infinitesimal amount. So this is equal to, now, I like to call that a broken derivative, but now with the delta H, this becomes a good derivative, or it becomes a derivative, let's say, because this is really not a derivative. So that's delta H over delta T, and that's dH dt, and that's the heat capacity at constant pressure. It's a very, very nice result. However, water doesn't really expand that much when it's being heated. So in that case, we can consider this term to be approximately zero. And by doing that, we can see for water, the delta H is approximately equal to the delta U. So this is going to be equal to, well, we can take the delta U delta T, and that'll give us the derivative of the internal energy with respect to temperature. But you see, in this case, we consider the volume as being a constant, so that's the heat capacity. That's the heat capacity constant volume. So for water, the heat capacity constant pressure is very close to the heat capacity of constant volume, since there's not much of a change in the volume. So we will write down the heat capacity constant pressure for water is the heat capacity constant volume. And if you want to divide by your mass, you will have then the specific heats. So for small delta T, I can write this heat capacity constant pressure as Q P over delta T. And that way I can write down QP is equal to the heat capacity constant pressure times delta T. But QP is delta H, so we can consider this as our delta H also. But this is called sensible heat. I like it in this form where I do not invoke any equation of state. For example, there's no equation of state that would be like the ideal gas law. So this is sensible heat. But since this sensible heat, QP, which is equal to CP delta T, that's equal to delta H, I would prefer to use the terminology here as we go to this lower equation. This is called the enthalpy of heating. And historically, that's sensible heat, and you can often find that everywhere on the internet. But I like to use the term enthalpy of heating. Now I would like to consider what historically originated as latent heat. And here we can think of evaporation. So here water, liquid water, you can put the water, say, a bit of water on a table, and after a while it disappears because it went into vapor form in the environment, where the environment above the liquid water is warmer. So we're all familiar with that, how a little bit of water on a table will disappear. Now in that case, we had the situation where the delta T, there's no temperature change. We have a phase change. We're going from liquid to vapor or to gas. And also the pressure is not changing. So the heat transfer here, I'm going to write down Q with the subscript liquid going to vapor. And since this is happening at constant pressure, this is going to be equal to a change in enthalpy. And I'll remind us we're doing liquid to vapor. Now, I would prefer here that we call this heat transfer the enthalpy of vaporization. So in each case, we have a Q sub P, so we have a change in enthalpy. Now we could call this as the practice to use a capital L sub V to mean the heat transfer required to change liquid water to a vapor. And delta H, we could say, well, there was the final, which is the vapor, minus the initial. So delta H is your final, delta anything is your final minus your initial. And here we have, in the final state, vapor. In the initial state, we have liquid for a given amount of liquid water that has evaporated. And this is the enthalpy of vaporization. Now we can look at the specific enthalpy of vaporization by dividing by the mass. So if we want specific, we divide by the mass, but note that the mass of the liquid is equal to the mass of the vapor, same mass, and we could just call that little m. So dividing both sides by little m, we then get little l. Remember, we divide by m and have specific, we use lowercase letters. So this is lowercase l sub v, and this would be a lowercase h sub v minus a lowercase h sub l. And this equation here will be important later for us. We'll use it, and this is our equation 18. So think of this as the specific enthalpy of vaporization. And now I'd like to do one more thing here, and that is the change in the specific enthalpy of vaporization. So in that case, we take a derivative. So we have dLV, and the change is with respect to temperature, the change in specific enthalpy of vaporization as we go to a different temperature. So this will be dHV dt minus dHL dt. Now, we don't have an equation of state for the liquid, but nevertheless it'll have an enthalpy, and we'll have a, say, dHdt for the liquid. Now at this point, we can remember an equation we had derived. The specific heat at constant pressure is the change in the enthalpy with respect to the temperature. That's our equation 16. And we just showed up here that the big C at constant pressure, the heat capacity, is d big H, d temperature. So if you divide by the mass, you would have this relation, the little c, so P is d little h, d T for temperature. So we can write down the derivative, or the change, and specific enthalpy of vaporization as this really nice result. It's going to be the specific heat at constant pressure for the vapor, which now I'm going to have to add another subscript, V for vapor, and then minus the specific heat at constant pressure for the liquid, which I'll use L. This equation is our equation 19. And that will conclude our class for evaporation.